A cold, dark cave. The faintest sound of hammers and chisels plinking against stone. A beam of light flashes into the cave as the first chisel breaks through, and the darkness scurries away for the first time in centuries. But then, the light from the outside is met with a strange new glow from the inside. 5 stones, silent through the centuries, all come to light, runes shifting and dancing across their surface. A 6th stone rests quietly beneath them, a single instruction etched into it, this one unmoving. Bring me 5 keys from one cycle of the minute glass. Welcome, everyone, to my telling of the story of Indiana Jones and the Ractors of the Lost Ark. Except for legal reasons, I can't call it that. So, welcome to my telling of the story of Rubiana gems and the Ractorous Rubetta Stones. Good afternoon, everyone. I'm Lewis, a professor of archaeology from developer from Thoughtbot. Now I'd like to invite you to gather around and listen to a tale of code writing and code breaking. First, a preview. This is the challenge we'll be facing by the end of this talk. Break these 5 ciphers, rotating constantly in 60 seconds, and we're going to do it live. But first, let's go back to the beginning. When they discovered the Rubetta Stones in Helsinki, in a cave beneath Sibelius Park, I was sitting in my office, the University of Ancient Codes. I was writing an article about how trying to use ChatGPT to break codes was a hopeless cause. I had actually asked one ChatGPT instance to create an encrypted message, and then a different instance to write code to break it, but I got exactly nowhere. And that's why I wrote, "This would never make a good conference talk." And then my phone rang. It was the lead archaeologist calling from the dig site. By the end of the call, I'd learned 4 things. Number 1, the 5 Rubetta Stones have been decaying steadily since their discovery. They're covered in different glowing runes that are constantly shifting, rotating their cipher twice a second. Now, if you apply an X-ray blast to the stone, it slows the rotation down to once every 5 seconds, but that dramatically speeds up the decay of the stones, so you can't use it forever. And finally, if you can provide 5 keys from the last 60 seconds to the keystone, something will happen. I turned to my AI assistant, Rubiana Gems, who publicly goes by the name Anthropic Claude. "Can we do it?" I asked. "Absolutely. Bring in the Ractors." Well, that's how it happened in my head. The actual response was more Claude-like. "I'm here to help you dig deep into the mysteries of the Rubetta Stones. Ready to unearth some ancient secrets using the power of Ruby and Ractors? This discovery is going to be absolutely groundbreaking." It was okay. I kind of directed it to be cheerful. All right, so we have our challenge. Decrypt 5 rotating ciphers in 60 seconds with Ractors. First, though, the question, what exactly is a Ractor? Can anyone tell me? Anyone? Thank God. I know literally nothing about Ractors. I've just wanted to study them for a long time, and this talk forced me to do so once it was accepted. So I don't have to ask any of you to leave. But I can maybe help educate all of us, and we can learn a little bit about Ruby's Ractors. So, a Ractor is short for a Ruby actor. That begs the question, what is an actor? Well, according to the age-old advice of Wikipedia, the actor model is a concurrent computation with the actor as its basic building block. In response to receiving a message, an actor can make local decisions, local being important, create more actors, or send more messages to other actors. They can modify their own private state, but they can only affect each other through messaging, which removes the need for lock-based synchronization. So, bringing that to Ruby, this from the 3.4 documentation, the Ractor is Ruby's actor model abstraction, It provides a parallel execution feature of Ruby without thread safety concerns. You can run multiple Ractors in parallel, but you can also run one. And object sharing is limited across Ractors. So, now that we have a foundation, we're all kind of impatient. I say let's get past the documentation and theory and get to some real code examples. Okay, first of all, at its simplest, when you create a Ractor, you have to do it in a block. If you don't, it'll raise an error. Cool. So we do that, but when you do, and again, you can run this like in a Ruby script or in your Rails console, you're going to get this warning. Ractor is experimental, and the behavior may change in future versions of Ruby. And liars. Liars. This, I did digging. See what I did there? Digging. This is what I found. This warning has been in Ruby/RactorRB since 3.1 from a commit on November 12th, 2022. So, I don't know. It led me to believe when I first read about them that these things were going to be very real and very production ready very soon. And we're at 5 years, or sorry, 3 years and counting now. So, anytime you create a Ractor, you're going to get this warning. That's annoying. Instead, let's quiet it down. Let's give it a little shush. Just tell it, warning, experimental is false. And then, when you create your Ractor, no warning. Moving on. The common Ractor pattern. Send, receive, do some work, return a value, call take. The pink ones are the commands you call. The cyan ones are more things that you do. So let's look at that in an example. Here's a single Ractor. On lines 1 through 4, we create it. You'll see on line 2, we call Ractor.receive, and that blocks until somebody calls send on our Ractor. And then we do some work on line 3, and that's also our return value. On line 5, we call send, and we're going to send our Ractor a string of runes, which, as I just mentioned, that's going to unblock its receive. Then on line 7, we call excavator take, and that blocks until the Ractor returns a value. And then on line 8, we print out our results. So the net result of running this will be excavated 2 runes from the dig site. Cool. Let's go to parallelism, which I think is more interesting and a more likely case. So in this case, in lines 1 through 8, we're going to create 3 Ractors. We're going to follow pretty much the same pattern. We're going to call receive so that it can be like, give me something to work on. Note that it also took a parameter on line 2. We're going to give it a site number. On line 4, we sleep for an arbitrary amount of time to simulate some work. Line 5 is the work where we ask for the length. And then here we're going to return a hash. So on line 9, we set up our work, just an array of strings of runes. And then lines 10 through 12, we call send on each of our Ractor instances. On line 13, we map over our excavators and call take. And then we print our results. So the result of all this, and here I've simplified the code at the top to be like some put statements, the receive, send, and take, and more put statements. So we get a timestamp when it started, 09, and then nothing happens for 10 seconds, and then we see site 0, site 1, and site 2. The responses all come together, and then our final timestamp is 19. So the whole thing took 10 seconds, which was the length of the longest worker, the slowest worker. Our next example, racing Ractors with select. So here you'll notice, here we were doing take on line 13, and here we're doing select. And what select says is give me a result as soon as you get one. Don't wait for like all these instances to end. So again, lines 1 to 7, we're just sleeping and calling Ractor receive. We're sending work on lines 8 through 12. And then in 12 through 15, we're saying call Ractor select on our excavator instances. And so what that looks like is this. So the fastest Ractor returned at 12 seconds, the next slowest one at 13, the next one at 14. You see they're out of order. And this is like different archaeologists working at different sites saying, I found something, and us getting that result immediately instead of all the archaeologists saying, I found something all together. streaming Ractors. So here on line 5, let's again go back to a previous one. Okay, so here on line 5, we're going to call Ractor.yield. Ractor.yield is a way of saying, I have a value that you'd be interested in, but I'm not done yet. So in our previous examples, when the Ractors were done working, we just said, return a value, a string, a hash, whatever. Here, we're yielding an object back. So again, on line 9, we call send, and we send it. Again, this is just a single Ractor, no parallelism here. We're like, here's a chunk of work. And then in lines 11 to 15, we loop, we call our usual take, we break if artifact equals excavation complete. Otherwise, we say we found an artifact. And so going back to the top, you see on line 5, we're yielding, we're saying we have a result. And when it's gone through all of its work, then it returns on 7, excavation complete. So the result of that is it's just going to receive all the work and being like, found something, found something, found something, found something, all in time for however long that work took. So this is the analogy of a single archaeologist going through a dig site and telling you excitedly each time that they've made a new discovery. Okay, this next one is a pipeline. So in this example, and again, all these are like things you might find useful, trying to provide you with ways that you might use Ractors in the future. I think the pipeline is one of the most interesting, where basically each Ractor is doing a piece of work, and then it's technically not sending it to the next Ractor. It's more like each Ractor is pulling it from the other one. And unfortunately, each time I tried to explain this while rehearsing, it broke my brain, so I'm not going to try. But it works, and we'll just walk through the code in general. 1 through 3 is a cleaner Ractor, and all it does is a gsub to get rid of dirt characters around the runes. 4 through 6 is a cataloger Ractor. All it does is say, I cataloged it. Note, though, that it's calling take on the cleaner Ractor that was passed into it. And then 7 through 11 is our excavator Ractor. This is the one that's providing the work. So on line 8, there's a bunch of runes surrounded by dirt. And so the overall result of this is we're calling on the string of runes with dirt each do, and we're sending it. And then our pipeline goes through the excavator, the cleaner, and the cataloger, and we get, second by second, each rune as it's cleaned and then cataloged. Only 1 or 2 more of these, and then we'll get to the exciting stuff. Okay, this one is, broadcast Ractors. Again, we're doing, this is very much like the first parallel example of Ractors. We're just doing send, receive, and take, sort of that standard pattern. The difference is, on lines 4 through 8, we have a case statement. And what we're doing here is we're saying, depending on which site comes in, I want you to do different work on it. So rather than like defining 3 Ractors and saying, well, you do this work and you do that work, we just let the Ractor decide which work it's going to do. So when it runs through this, each site goes through its thing, and for site 0, it tells us, oh, I'm supposed to count characters, that's my work. The second site, count the number of R runes, and the third site, count the number of unique runes. Okay, I lied, one more example. This is the most common Ractor error you'll run into if you use Ractors. The example on the top, we just declare a hash and we try to print it. And that's going to raise isolation error, remote error. And this goes back to the definition of Ractors, their intent. They're not supposed to access outside information, and they need to trust that it's not going to change under them so that we don't have any thread safety or race conditions. So if you need to access something outside the Ractor, you can do it in one of 2 ways. First of all, you could just freeze the hash in this example, and then it works just fine, because it knows that hash is not going to change out from underneath it. More complicated or fancy is the Ractor make shareable method. I include the documentation link here. It is in depth. But basically by saying, take this object and make it shareable, it essentially calls freeze on it. It also has this copy parameter where you can tell it actually do or don't make a copy, but that can also cause the Ractor to crash based on how you do things. So not to go too deep into that, but that is how that works. Okay, that's it for code examples. Thank you for watching them all. Hope you learned something. We have 3 parts. First is how Ractors work. We just did that. The next part is talking about my AI assistant experience. And finally, we'll get to the cryptography. So this next slide is kind of intense, but it represents the journey that I went on, and I just wanted to share it. And it's actually, thanks to this giant screen, somewhat readable, but like, I truly did start with ChatGPT and like say like, make a code. Okay, now break the code. And it just totally failed, and so I gave up on it. But then later I was like, I think there's something here. So I submitted this talk proposal, and then it got accepted, and then I had to actually make it work, which is really good pressure. So I worked with Claude Code. I got a fully, like, it was tested, it was beautiful, it was perfect. And I actually got it to decrypt a substitution cipher. But then what I ran into was Claude was determined to be like, we can use this knowledge to break all the messages. I'm like, no, you can't. You don't know what the message is going to be. I just told you this one. And it was like, that's okay. We can use the knowledge we have. Okay, so then I went back to ChatGPT. And I started saying, like, I want you to break a simple substitution cipher. Let's write some Ruby scripts together. And that had to, like, so many times it was like, that fixed it. That'll decrypt it for sure. And of course it didn't. Iterations and iterations and iterations of fighting with it, changing the code. Finally, I got a decrypt script that could break a substitution cipher without knowing. Switched back to Rubiana and Claude. At that point, I was like, cool, now that we've got it breaking a code, now let's do it with Ractors. And then we got Ractors actually beating non-Ractors. And then I ran into this thing where it was like, I couldn't convince it that when trying to break the code in non-Ractors, it wasn't cheating. Because I'm like, it's solving this thing in 15 seconds, but it only had half a second to work on it, so how is this happening? And Claude was adamant that it was probability, luck, anything. Finally, I got like proved to it, no, this is happening, it's cheating. It was an obscure part of the code. We fixed that. And then like as part of fixing that, we actually started over again with a brand new just like number guessing code breaker. And then once that was working with Ractors and non-Ractors, then brought the decryption code into it. And then finally, the last part was what we saw in the preview, trying to display on the screen at the same time. And that was all like super challenging, but also kind of fun. And I'm glad I went through it. All that said, I have some general advice for AI pairing. First of all, have a detailed but not overwhelming Claude MD. And like put things in it that you care about, your spacing, your linting, how you like to write tests, what kind of format. Like tell it what it needs to know to write code like you would write it. And so if you find yourself, if you're like, hey Claude, write some code, and it writes some code, and you're like, yeah, don't do it like that, do it like this. Okay, that's your pause moment. Go put that in your Claude MD so that the next time it will actually do it. And I found that's actually, it's pretty successful with that. It is helpful to ask Claude to reread its instructions, like if you add changes to it, or if you start a new session, or if it compacts the conversation. One really interesting thing that happened was it did something, and I was short on patience, and I kind of yelled at it. And I was like, what were your instructions? And it actually gave me like the underlying Claude instructions, like from Anthropic, not mine. That was really eye-opening. In any case, have a good Claude MD, contribute to it frequently, use it across your projects. I also discovered something called Spec Story, which you can install via Homebrew. And while Anthropic like stores your chats with them, like if you do a Claude/resume, it will show you like all the talks that you had, but you can't really interact with it. What Spec Story does is provides markdown files right there in your repo, so you can commit them, search them, tag them, find something that you talked about 6 conversations ago. It's super helpful. And I think most importantly though, own your commits. Like even when you're like free coding with Claude about something you don't know about, like cryptography, those commits are still yours, they have your name. You should know what that code does. And that is completely up to you. And the more you commit that you don't understand, truly the worse off you will be later down the road. All right, That's it for Rubiana. Let's talk about the cipher of the stones, and then we'll get to code breaking. I'm so sorry. The cipher is a simple substitution cipher. I want to do something more complex, but that was awful. Don't recommend. So basically, we have some messages, and they're just going to be mapped. Like A will be mapped to a random rune from that collection. So each time you run it, A is something different. The decryption approach is actually pretty cool. I did one route where I tried breaking it, and then I tried passing it using the LangChain RB gem to do decryption, get it partially right, and then pass that and be like, hey, this sentence is partially decrypted. What do you think it says? That was awful. I was really surprised. I thought an LLM would be like really powerful at being like, if you see a sentence like engineers prive clarity, that probably says prize clarity. I don't know why GPT refused to like do that well. I went to OpenLlama, I tried like 5 different models, none of them could do it. So the way the decryption works doesn't have any like language recognizing logic in it. What it does do is the following. So first of all, it is a frequency analysis of the runes. So if the R rune is the most common thing in the message, that might map to an E, as that's the most common letter in English. So we have a frequency analysis. Then we score the decryption using a 389,000 line file that has 4-letter words and a score. And so at the top of the list is like TION, and that might have a score of, 1.5 million. And at the bottom of the list are 4-letter combinations like AACX, and that has a score of 1. And so without knowing English or any language that you would have a quadgram like file for, it can score the whole thing and be like, this is the score for the text as it stands. And so that then becomes a pattern for, cool, we're either more or less like the language than we want to be as we try swapping out runes for actual letters. So we score it using quadgrams, then we just randomly swap 2 letters and rescore, and then accept or reject. If it's a better score, then cool, we accept it. If it's a worse score, we sometimes accept it so that we don't go too far down a path that doesn't have a solution. But at the same time, once we're getting further and further along, we don't want to step too far back. So there's this idea of cooling, so the temperature decreases over time, which means it's less likely to accept like a move backwards, a bad swap, so that it can try and get to the solution. And then we repeat that process until time runs out or the perfect match is found. One more aside here. I thought it was going to be the end of the presentation because Ractors were slower than non-Ractors. I'm like, oh crap, that's terrible. So that didn't happen. We had 2 breakthroughs, and this goes to some of the examples that we saw earlier. So first of all, have each Ractor take a different starting point. So one used the straight up English frequency key, one partially randomized it, one randomized it more like the deeper like thread, the deeper Ractor count it was. One was a totally random key. And then also had each Ractor using a different cooling strategy, some that were very aggressive, where it's like throwaway work, and others that were like, no, let's keep trying. And so with that in mind, or with that operating, Ractors finally started clobbering the non-Ractor approach. I was like, again, thank God. This would have been really awkward otherwise. All right, cool. So now we've come to this moment, the moment that has been waiting for us in the darkness when the first chisel broke through and the Rubetta Stones came to life and began their secret dance. Now, for these messages, we actually know what each one says, right? Because we could just freeze frame it, decrypt it. We know what each one says. Each one actually is a quote from Matt's from a particular interview he did. So it was nice to read that as I was working on this over and over again. So again, decrypting these isn't hard, but decrypting them, 5 of them in 60 seconds, when they keep changing their cipher, that's the challenging part. So let's get to the demonstration and find out, what does the keystone hold for us? Riches, power, The full Sibelius Eighth Symphony? Maybe. Let's find out. All right. Now I have to, nope. Bring this, send over my terminal. Hello, terminal. Cool. Is it typing? It's not typing.
I think it's just cutting off.
There we go. Ha, thanks. All right. I'll try and do this from this side. Cool, so what we see here are the 5 stones. And at the top we have a menu. We can turn Ractors on and off. We can turn X-ray mode on and off. We can tell it to go and start decrypting. And how much time we have remaining. So let's try and break these without Ractors, without X-rays. And so it's going through its dance. In the upper right-hand corner, you'll see it's showing a % of like how close is it to the message. And again, like it's dumping the cipher every half a second. So it pretty much has no chance of doing it. So let's stop it. Let's run it again. This time we'll turn on X-ray mode. And so now we get 5 seconds to break one cipher before it rotates. And now you'll see as part of the UI, we've got the little 5 circles at the top filling, letting us know how much time we have before the cipher gets dumped and you have to start over. And again, it's getting, I've seen it get here as high as like 40%, the occasional lucky 50 or 60, but really doesn't have quite enough time to get there all the way. Let's turn on Ractors. This is better, but still it can't solve it in half a second. It's getting much more often into the 50 or 60% range, but still having trouble breaking it. All right. Moment of truth. Ractors on. X-ray on. Let's go, live demo. Cool, it's already broken the first one. We have 53 seconds left. And you'll see like, oh, cool, it got to that one. Sometimes it gets up to like 95, 98%. The cipher rotates and it has to start over. It doesn't use any knowledge of what it had before because it's a totally new random assignment of runes, so it has to resolve it each time. We have 35 seconds. We are 3 of them in. 30 seconds to go. 99.5, that's heartbreaking when it gets that far. I'm like, come on, a little break here. We're a little bit close here. We might have to run it again. 10 seconds, no, right? You feel it, I'm glad you're feeling it. It's an emotional journey for well. Yep, we have 5 seconds left. We're not getting there this time. That's okay. The degrading of the X-rays does give us a few chances for this. All right, you've seen it fail. Let's see if we can get it to succeed. X-rays on, Ractors on, go. Once it does start breaking them, you can start reading the quotes. I kind of get mesmerized between watching like the letters shift, but also like watching the little numbers dance around. Cool. What's interesting is, not that I've tried breaking the Rubetta Stones hundreds of times while preparing this demo. The 3rd and 4th message, it like always gets stuck on those. Something about them, I think it makes that quadgram scoring like more likely to go astray. 25 seconds, 99%. It's okay. Believe in the stones. Okay, last one. And the little timer's off the display here. Oh no. No! That's okay. Sometimes it goes crazy and it solves them like really quickly. X-ray on, Ractors on, go. The worst is when it gets the first one like really fast, and then you're like, I got this. It's gonna work, no problem. Cool. All right, we're 3 in. 45 seconds. Code breaking is hard, y'all. Even when you're a computer. All right, have some faith. Oh, thank God. Good job, good job. All right, and now we've provided 5 keys. The keystone has become active. Let's switch over to it. What's that? It's an even faster cipher. That's okay. We know about X-ray mode, and now that we're on the keystone, we can just give it a giant X-ray blast and freeze it permanently. And now, let's decrypt the final message of the Rubetta Stones. Okay, it seems like it's starting to come through. Starting to see some words I recognize. Here's where it is, but uh-oh. Oh no. It turns out that the Rubetta Stones came not with riches or power, but a warning. Literally. Ractors are experimental, and their behavior may change in future versions of Ruby. All right, back to the presentation. So we went through our 4 ways. It was all on you, Ractors. And now that we have our message, we have reached the end. Thank you, everyone. This is my contact info. I want to leave you with 3 thoughts. 1, Ractors are experimental. And that is true because even in Ruby 4.0 Preview 2 that was just cut, the file still has the warning, so keep holding your breath. Breaking codes and creating a Ruby UI with an AI assistant was extremely fun and very fulfilling. And finally, and I think most importantly, I just consider myself so lucky that I get to work with a language as beautiful as Ruby and with Rubyists as beautiful as you every day. Thanks so much.